might need to use that. Can you hear me? Okay, I'm Aparna Ganguly from South Texas College. I'm here to introduce our speakers, Jay Martin and Tsai. And Jay is currently teaching at mathematics at Wake Technical Community College in Raleigh, North Carolina, where he has taught for last 27 years. He has been a long-time active AMATYC member, his last assignment being AMATYC exhibit chair during 2003 to 2010. Jay believes mathematics should be presented in context. Other interest includes, you don't want that, right? Use technology appropriately, and extended projects should be assigned in all courses. And there are some hobbies he has, and he said, don't have to mention. Okay, so I honor your wish. Okay, here is Bev. She is currently teaching in mathematics with same college, Wake Technical Community College in Raleigh, North Carolina. She has been there for 20 years, so they are colleagues for last 20 years, right? Okay. Being the parent of two teenagers, Beth understands the millennial student and strives to create a classroom environment that appeals to people with a variety of learning styles. In addition to her full teaching load, Beth is the sponsor for the school's math club and likes the challenge of successfully preparing her students for state and regional math tournaments. In her spare time, she enjoys reading, craft projects, gardening, and studying. Give a big hand. Here are our speakers.
Hello, my name is Beth Tsai from Wake Tech Community College, and we're going to be talking about calculus and pre-calculus projects today. If you notice, we don't have any handouts for you, so you'll want to take note of our email addresses. If you are interested, we will send you a copy of the PowerPoint presentation as well as copies of the Word documents that we hand out to our students. We did that in order for you to be able to customize these to meet your students' needs. All right, so I'm going to start the presentation by asking you all a question. I'm going to poll the audience. Who in here currently uses projects in their classes? Wow, I would say about less than half of you do. So I'm glad you're here. So you're coming here to learn more about it, right? Okay, we have been using projects in our classrooms for probably the last 15 years or more. And what precipitated it was a document that came out Beyond Crossroads. And so let's look at some excerpts from that document. This initiative said that we need to create courses and activities to promote students' ability to use multiple approaches or representations to examine mathematical concepts, extending the concept for students. Require group projects, group discussions, and explorations in your classrooms. Expect students to communicate orally and with written reports. And lastly, use technology to give students expertise with those skills that they will use in their careers. Now, we took this and we decided that projects were the best way to try to implement these action items. And so we're going to talk about 4 projects today, and I'm going to turn it over to Mr. Martin here, Jay, and he's going to have one for you.
The other nice thing about projects, it allows you to go to conferences and your students are home killing themselves trying to figure out these projects, and it gives them something to do. In fact, last Friday I had my pre-calculus students do the parachute project. So they built parachutes, dropped them off second floor in one of our buildings, collect data, and rather than me telling you about that project, I'm going to show you the video that shows you exactly what they did. Now, creating this video, I'll tell you a little funny story that happened. I'm telling them what to do. So this group of students, I said, you know, take your parachute up to the top floor, drop it off, and we're going to hold a CBR underneath it and collect free fall data. Well, one of my students gets down on the floor and starts taking her shoes off. So I look at her and I'm like, what are you doing? She said, well, you told me to take my pair of shoes off and take them up to the second floor and drop them off. So she literally thought I said pair of shoes. So. Okay, so each group had 5 parachutes, and within those 5 parachutes, each group had a different mass. So that's where we extend this project to Calc 3. So let me just show you the results of that students would do in pre-calc, and then extending this to Calculus 3. So sample data, surface area of 6 parachutes with the velocities. And that's a scatter plot of them. So they're trying to model this data so they can make some predictions. So we use re-expression. So if it's a power function, then we would use the natural log of x and y to try to re-express to make it linear. If it's exponential, then just the log of the y's would make it linear. So rather than just hitting exponential or power regression, we teach the re-expression because it requires it in Calc 3. So this is just the natural log of the surface areas. You can tell that the re-expression is not linear. And here's the natural log of both the x's and the y's. Data is fairly linear. Correlation of square root of 0.98, so fairly high. And so that's the linear equation they have, but they're putting natural log of y and natural log of x in for x and y and mechanically go through. And they get a model. So 113 divided by x to the roughly 0.5. And that's a graph model versus the scatter plot. Now in Calc 3, my students just take the data, and now it's in 3D, so each group of parachutes had a different mass. And all 5 sets of parachutes had the same, surface area. So group 1 had 5 different parachutes of 5 different surface areas, but group 2 had the same 5 surface areas but a different mass. So they're given terminal velocity, surface area, and attached mass. They're trying to find the terminal velocity as a function of those 2 input variables. And they're going to use re-expression and linear regression on Excel. So in multi-regression, it'll only do linear. So that's why we've got to take this curve data and build it into a linear data set by re-expression. And then they can make some realistic predictions. So this is the format of graphing in Excel. We use that software to plot this data. So you put your x's and y's and then your z's in the middle, kind of like a multiplication table. And that's the Excel scatter plot of this surface. So you see it's kind of bowed a little bit. Now to be able to do linear regression in Excel, you need to have it in column data, so it takes a while to reformat all that data. But now they have 8 re-expressions to do. So they can take the natural log of just the mass and leave area and terminal velocity alone. Or you can do, linear regression of mass and area and leave the terminal velocity alone. So there's 8 different combinations. So they go through and they do all 8 combinations, do multi-regression to see which one produces the most linear surface or the highest correlation coefficient. And this is the one that actually produces the best results, the natural log of all 3 variables. That's the output that Excel creates for them. The coefficients, you have an intercept of 2.48 and a coefficient on the ln of mass, the 0.54, and the negative 0.49 on the natural log of the area. So, and then they go through the mechanics of undoing the linear function of 2 variables, solving for terminal velocity, creating 12 times mass to roughly the 0.5 power, divided by the area to roughly the 0.5 power. So that's a model that they can predict velocity from mass and parachute area. Now these parachutes were fairly small, so I asked them to go and extend it out to something realistic and just to test out the model. And actually it gives you fairly reasonable results. So if you take an average parachute of 24 feet, now these are just round parachutes, so not the sophisticated ones they have today that you can do a lot of different things with them. And if you take an average person's weight, so this is just off of the internet. I'm not going to discuss these numbers, but that's what it is. And so taking those averages and the model that they produce from the parachutes that you saw in the video, produces 18 miles per hour landing for a guy and 17 miles per hour landing for a female, which is a little bit faster than what you would expect. Okay, so I'm going to turn the next project over to Beth.
All right, this one that we're going to talk about next is a Calculus 1 project. And what you see there in the fun keeps rolling along is what one of the students called it. Now, what isn't fun is something that we have to do at the end of every semester. We have learning objectives in our courses. I don't know if you all do. And we collect data from our final exam on our learning objectives. And we try to do interventions on our 2 lowest learning objectives. So one of them is optimization, which this project deals with. Can you think of what the other one is for those of you who teach calculus? What? Related weights. Yes, that is the tie that binds us all together, isn't it? Yes, it sure is. So optimization being one of our low-performing LOs, I tried to come up with something to address it. So this is the project that came out of that. Now, when I took this project to my colleagues, one of my colleagues said, "Oh, I've got a great hands-on activity that I'm going to use to introduce this project." So you can read here, the students are going to use optimization techniques to explore designs for cylindrical storage containers. I want to show you what she did.
So today's activity is to get you familiar with the formulas you're going to need to do the big project. The surface area of a right circular cylinder and the volume, but you're going to mostly be involved with the volume. You'll get a piece of construction paper, a ruler, a compass, some Scotch tape, and a pair of scissors. And then you're supposed to construct a can of a maximum volume. And we have some bonus points for the students who get the maximum volume.
Inches or 8.5-inch circumference. Right. So the maximum that we need to find what our radius can be and find out how much space we have left over on our sheet paper. So circumference equals 2 pi r, and then 11 divided by 2 pi equals 1.7. All right, 1.2. Let's see what's up. Okay. And then we need to measure, see how much room we have left up to find out the initial volume before we cut it.
All right, the circle's circumference has to be, and we need to do it by going this way or 8.5 going this way. So we just equal each one. And we can see which way works better. If we take each week, so we go this way, 14, well, less we go, and this way we're bigger.
Yeah, how much we do the radius?
The radius comes out to 1.75 from 11.
Most the volume? What's the volume on this? 744.1 inches. And the height is 41.5 centimeters. Should be like 8.5. That was so many.
Okay, I'm going to stop it here. This group won, by the way. They had the largest can on that particular activity. Now, what you see here is that they are trying to maximize the volume given a fixed surface area. Now, the actual project involves trying to maximize the surface area with a fixed volume, because when you go to the store, you don't buy, just any type of volume. You buy 6-ounce containers, 8-ounce containers, so usually the volume is fixed. So let's look at minimizing the surface area with a fixed volume. And I have them disregard waste and material costs to start with. So then you've got the cylindrical storage container, which, we break down into the top, the bottom, and then cut and open up the sides, right? And you can see what the optimization problem becomes. We want to minimize the area, which we've got the area of 2 circles, and then plus the circumference of the circle, which becomes the side of the rectangle times the height, right? And then the volume is pi r squared h. Then I have them show that the surface area is minimized when the h to r ratio is 2. So this was a student response. Of course, they took the derivative, right, set it equal to 0, and got that h divided by r was 2. And then I said, well, let's think about this a little bit more realistically. What if we allow waste to come into the equation? So I kept the tops, the bottoms, and the sides out of the same material to start with. And so we've got a problem that looks like this now. So material is usually bought in rectangular sheets, correct? So then you would have these rectangular sheets all the way across. And this is what your optimization problem becomes. You've got 2 squares. So the side here, this is 2r by 2r, right? So you've got 2r squared and 2 of them. And then here's your 2 pi r, and there's your h. And then the volume again is fixed. And then I had them compute the h to r ratio for this one. So they took the formula, got it all in terms of one variable there with r, and then took the derivative with respect to r, and then did h to r and got 8 to pi. And then I said, okay, show me the money. So what we've got here is we're considering that the tops and the bottoms could be made and the sides made out of different types of materials, right? So to minimize your cost, then that's the optimization problem you want to look at, because just minimizing your surface area would minimize your cost if it's all made out of the same thing, right? So now we're looking at making it out of different stuff. And we have lots of things to consider here. They have different gauge materials for the tops, the bottoms, and the sides, sealing, pressing, we've got insets, cost of cutting, and all of those things. So we're trying to bring this into a real-life scenario. So this is an acceptable solution. Now what I like about this project, it is a little open-ended. Students looked at it very different ways. This would be one that would be an acceptable solution. All right, so they're minimizing their cost, and then I wanted to show you where this constraint function comes from. This one says if you have your volume in the end, it's got to be this. And so if you talk about what you're losing, the end result comes from loss in pressing and sealing and the indentation loss, and this is how this particular group interpreted this problem. Now, in the project, they would solve this symbolically. I'm giving you the graphical solution here. And then I had them compute the h to r ratio. Now, this is just for this particular scenario, but when you do this one, you get the h to r ratio to be 3.54. So I had, you know, h to r being 2, h to r being 8 divided by pi, and then I had h to r being 3.54. So then I sent the students for a fun activity to the grocery store. Okay, so I sent them there to look at different h to r ratios. And this was actual student response, which I thought was really cool, in color and everything. Okay, so I was really pleased with this. But they went to the grocery store, did the h divided by r's, and then compared them actually to this 8 to pi ratio. And these are what they came up with. Now, some of their conclusions were that they thought that the h to r ratio came closer to the 8 divided by pi when it was a bulk food item. They thought that maybe shelf space may dictate the shape of the container, because if it's tall and skinny, you can get more things in a shelf. Okay. And then they also said, well, you know, aesthetics, because you want it to look like you're buying a lot, right? So marketing and aesthetics can come into play too. So again, it's taking these ideas and extending them beyond the math and letting them think about the world around them. All right, Jay's got another one.
This project came out of a phone call that I received. I was grading exams at my desk several years ago, and a random phone call came in and said, I'm a local grading contractor, and I've been asked to give an estimate on filling this pond for this gentleman. And this pond is 300 feet by 150 feet, so it's elliptical in the top, 40 feet deep, and it's got sloping sides. He said, what's the formula for that volume? I'm like, well, I have no idea. You know, give me some time and I'll go try to find one. Well, I never found one, so I said, well, we will come up with one. So out of that phone call, we came up with a little activity here for our Calc 1 students. Is determining the cost for transporting fill dirt to such a pond as this. And if I'm not really sure about what costs are for trucks, I've made this up just to make it a little more interesting for them. So if we just take, what's that? Put a 1 in front of that 35? Remember that comment when we get to the end result of how much this would cost. And then the end result is for them students to come up with a formula that has all these different parameters in them. So A, B, the depth, and the slopes of the sides. So a volume formula for such a shape with all 4 parameters in there as an end result for them to come up with. So Beth and I very much teach Calc 2 and Calc 1 similarly when we start doing integration, because every integration application we do, we start numerically. You know, if we slice it up, you know, how do you calculate the volume of those slices? We even do force and fluid force and work all the same way. We break it up into slices, compute it numerically, and then generalize from there. So exactly how we approach this. So if we had 4 slices, 10 feet deep, I think these A values are at the midpoints of each 4 of those slices. So 145, 135, 125. So this is using a slope of 1 coming down the side of the pond. And then I give them the formula for the area of an ellipse, which is pi AB, so they can calculate those volumes. And then what happens if we break it up at 400 slices? Get a little more accurate, and then they can generalize it to come up with an integral. And that's kind of the end result they get there. So it's a fairly simple integral, and they're pretty successful coming up with it if they do those numerical approximations first, leading them to that formula. So cost estimate, it would take more than 2,000 trips to fill up such a pond that he gave me. So whether he actually did that or not, I sort of doubt it. Even at just $35 a truckload, they're talking $74,000. And back over to Beth for the last project dealing with Newton's method.
All right, this is a Calc 1 project, and again, that little subtitle is what my students, one group of my students called it, Stop the Insanity. Okay. So how many of you teach Calc 1? teach Calc 1? So we all teach Newton's method, probably. And I always wonder why in the world we teach it now. Because I go, don't we have a button for that, right, on the calculator? Because you know what Newton's method does. All of you raised your hand. It, finds the zeros of a function, right? So we thought, how can we jazz this up a little bit, extend the course content to make this an interesting topic for students? Well, we're going to play off of the fact that it is starting point sensitive. And we're going to introduce them to the world of chaos, hopefully. Now we start with a real root scenario. So let's consider this function f of x, which is x cubed minus x, and they factor it to get the zeros. So the zeros there, as you can see on the graph, are -1, 0, and 1. And we're going to color code them in this demonstration. So 1 is colored red, -1 blue, 0 is yellow. Now we're going to try to approximate a 0. And in this method, you have a starting point. So let me back up again to this one, back to this slide. I'm starting with, if I can get my hand here, I'm going to start with this particular starting point and see which one of these roots that method converges to. So 2 is our guess. And we have them find the tangent line to the graph and, of course, compute its x-intercept. So as you can see, the tangent line to the graph is 11x minus 16, and the x-intercept is 1.4545, which is right there. Can you see that 1.4545 is closer to 1 than you started off with? Yes, yes. Now, in Newton's method, and if I were in a classroom situation, I would derive it, but he automates this process of finding the x-intercept of the tangent line. So that's what his formula does here. And so with the formula, you could start, there's 2 is your initial starting point, that is the function at 2, and then the derivative there. And you get this. Now, I'm going to use Geometer Sketchpad. How many of you use Geometer Sketchpad? It is a cool tool. And I want to show you what I would do in my classroom to illustrate this. I can get it. Oops, I think I just lost it. So bear with me 1 second. So this is the graph of the function that we had, and this is the starting point 2. And when I click this, it's going to show the successive iterations here. So that's my next guess, which is 1.46. If I click again, it should show me the next one, and you can see that it's converging to the root of 1. So there's the last one, 1.03. So it's a nice illustration. So this converges to the root of 1, and what we say is that this 2 is attracted to the 0, 1, and we color it red. Now we have students automate this process on their calculators because the TI-89, which is what we require in our classroom, does this. So you'd say 2 store to x, and of course this is x minus y1 of x and divided by the derivative. We store it back to x, and we keep hitting the enter key, and it will just do this process for us. Now here's some student results. We have them investigate various starting points and then see where they converge. So this was the 2 that went to 1.4545 and eventually converged to 1. So these are their starting points, and these are where they converge, and we had them color them in the respective colors. And you can see very clearly that if you're over here, this one converges to 1, things over here converge to 1, things over here converge to -1, things over here converge to 0, and then we got some strange stuff happening right in here. So to lead them, we first have them find the critical points. So the critical points are where the slope is 0. So when you take the derivative, set it equal to 0, you get the plus or minus root a third. Now this would be a bad starting point for Newton's method, and why would that be for you all who teach Newton's method? No x-intercept of a horizontal line. Thank you very much. Also, if you look at Newton's method formula, you're dividing by what? 0. Dividing by 0 in the formula. Yeah, thank you. Then we have them look at bounce points. Now this is something that may be new for you. It's a place where if you start and you go one iteration, it'll bounce you back the next iteration. So we had students find it, and for this particular function, it's plus or minus root a fifth. Now I want to illustrate what happens there. So if you start at positive root a fifth, and you draw a tangent line, and you find the x-intercept of the tangent line, it throws you to this point. Right? Negative root a fifth, 0. And then you repeat the process. So you draw the tangent line at negative root a fifth, correct? And his x-intercept is positive root a fifth. And you would keep doing this. It's insane, isn't it? That's why they called it Stop the Insanity. So we had them look at what happened around the critical point to the bounce point. And this was a student's sketch, which I thought was really, really nice. And so they considered this interval, and what they found out was that small changes in your starting point, like 0.46, that converged to 1, while 0.47 converged to -1. So they're getting the idea that it's starting point sensitive. There's something going on here. Then we take it up to the complex plane. So the next thing we do is have them look at x cubed minus 1. Now, when you set that equal to 0, of course, that's going to give you the cube roots of unity, right? So let's look at this. There they are. 1 you can see on the graph, 2 you cannot. 2 are complex. So this gets us into graphing in the complex plane. So the next lesson is how do we graph in the complex plane? Of course, you have your real axis here and your imaginary axis. That's the root 1, and of course these are your complex conjugates. And depending on how fancy you want to get, you can talk about De Moivre's theorem. There's a lot of math that you could bring up here, right? We have them investigate at least 30 points here. And again, your calculator will do this even in the complex, with the complex numbers. And we see what they converge to. Now here are your roots in the diamonds. So there's the 1 again. There's the complex conjugate pairs. And you can see the basins of attraction. So if you have starting points that are in here, they're going to be attracted to this root, this root, and some of over here, the yellow one. And so that's why it's colored red, blue, and yellow. But something really interesting happens when you get along these boundary lines. And so once they start zooming in and getting closer and closer to the boundary lines, they should see something like this appearing, which is a fractal image. And it's really cool to watch them discover these things. Now, to get a close-up of that, of course, they discovered that there really is order to chaos. And we have them go to this website. This website generates fractal images. And of course, this is the fractal images for the cube roots of unity. Now, if you look at the other fractal images here, you've got the 4th roots of unity, the 5th roots, and so on. So it's a really cool way to put some life in an otherwise stale topic. All right, so again, these are our email addresses. Please feel free to email us. We'll send you copies of the presentation as well as all the student handouts so that you can tweak them for your own classes. Are there any questions or anything for us? Yes, sir.
I have to ask a couple. When I cover Newton's method, it's literally almost as an afterthought. And to spend this much time in detail on that, how many credit hours are your calculus courses? Because I can imagine having this much time to do all this in my calculus class.
We used to give full projects a semester, say 5 to 10 years ago. We have cut that back to one semester project. We do not spend any time in class doing it. We introduce the project to them and go for it. You have a month to pull it together. You know, they can come see us in office hours and whatever, but this is not class time. We introduce it, boom, you pull it together and work on it. So it's not taking class time. And we have 5 hours a week with them. Or
5 50-minute.
5 50-minute classes with them.
Any other questions? Yes, ma'am. Okay. Yes,
for
I
the
want to make sure.
parachuting.
She asked what tool they're using to collect the data.
Okay,
Yes.
it's a CBR. It's a sonar device that is hooked up to a TI. Well, I had it hooked up to a TI 86. You know, you can hook it up to 84 or 83. But it's a motion detector, CBR.
Any other questions? I have one for you, for those of you, the small percentage of you that do projects. I wanted to pick your brain, like, how do you assess projects? Do you do a grading rubric? Do you give everybody the same grade? Just a couple of, I want to get something from you before I leave. Before you leave. Yes.
One thing, if you do group projects,
Mm-hmm.
different members of the group contribute differently. So you can tell the group they have 80 points to split up between them, and they have to decide who gets these points.
Okay. So 80 points between them, they have to decide.
The value of the project is. It's a 100-point project, they did an 80-point response. They have to then divide the points, and then you can
Do it out of 80 to get your percentages. That's a good idea. Yes, ma'am.
I work very closely with my groups when I put them in groups. I don't only like active interns around who do their group project, and then I know them. And I put my C students together, I put my A students together, and I don't let them form their own groups. And I had some guys who wanted to grab one of my A students, one young girl, and they were kind of intimidated because she was just a little sweetheart, a little cupcake. And she was, you know, just an easygoing kid. And I pulled her right out of their group and I said, oh no, you don't get Amelia. She's going over here with the A students. And they were like heartbroken. I said, how? And so that's how I control that they're going to have to contribute because they're all pretty much equally capable in calculus. And then I work very closely with them. They have to come into my office and give me progress reports. If they miss a progress report, then they lose points off their project.
Yeah, I'm a big proponent of interim deadlines. Yeah.
And I'll fire somebody, and I'll tell them, if I see you goofing off on a group, you are fired, man. You're out of here. We're not going to waste time on you.
some of my groups did vote other members off the island.
The tribe has spoken.
I waited and fired people.
Yes, ma'am.
One thing that can be done if there's like 80 points for a group to divvy up is if you have each person in the group submit their idea of who put in the most work. And so if you get 3 people saying, you know,
Yes, we do that.
did the most and that one didn't do anything, but
Yes.
that one tells you they all did the same.
We do peer review. Yeah.
A closed ballot is probably better than open discussion.
Yes. And I think there was a question over here or a comment. Yes, ma'am.
We use rubrics
We do.
for our projects, but there's so many details within them because then, you know, a full day sometimes to grade them. And also there's a problem of, one student doing a lot of work.
Yes.
So we usually check rough drafts,
Yeah.
If we give 3 weeks or something, we'll have each student read their own rough draft, and it, of course, doesn't, kill all problems because, they do it often, it can't be a perfect situation, but it is time consuming.
Mm-hmm.
And I think because we put them in groups maybe of 3 or 4, that sort of cuts down on the time to grade the project, if you use rubrics that contain all the details when you grade it, but
Do you all use project quizzes? Like we do that too on occasion. Like when you turn in your project, there's a quiz on it. And so I can test whether or not a student has basic knowledge of what they did in the project by giving them a quiz when they turn it in. All right. Yes, yes, yes.
The other thing I do is
Oh.
I'm sorry.
I'm sorry, that's okay.
One of the things that I do is break their grade up into two pieces. And one piece is how well did they solve the problem, and the other piece is how well did they write it up.
Mm.
And so there's a percent, and it's usually something like 75-25% on the math and on the writing. And then as far as the math goes, there's a list of things they're supposed to do, so you make sure they've done all of these things. And I have them do individual drafts, so that if someone complains that this person didn't do any work, I can look at their draft.
Good. Good. And you had another comment?
Oh, when I do their presentations, it's a large project that's taken up a lot of time for the class. They do their presentation of their work, and I invite the other math teachers in, the other math professors in the meeting, and it becomes like a little colloquium for them. And that sort of puts, feel in their mind that they better be up to snuff and be able to answer questions. And the math professors pepper them with questions, so everyone out there presenting has to know their stuff.
Great. Well, one more.
I have a question.
Oh, you have a question? Good.
For the parachute project, have you ever teamed up a Calc 1 and a Calc 3 and just had them visit each other's classes and show the results of their two perspectives on analyzing the parachute?
Did you all hear what she asked?
Can you say a little bit louder?
She wanted to know if you had the Calc 1s and the Calc 3s to visit each other's classrooms.
No, I haven't. Usually in my class,
That would be a cool thing to
I
do.
take the parachute in and say, this is, what they dropped, this is the data that they gathered, and you guys go run with the data. So.
Was there another one, a quick one over here, or a comment? Yes, yes, sir.
We're right across the street, basically, from the University of South Florida, and they've been doing a lot of brainstorming to try to figure out how to get success rates in their calculus sequence higher. And one of the things that they've been trying are for selected students in lieu of the final exam to do a personal project, just to get more interest in the material. Have you guys ever tried anything like that or thought about moving that in that direction possibly? How would you feel about that?
Yeah, I don't know.
I don't feel very comfortable with replacing an exam with a project. Because I want to know what that individual student knows when they exit my class, because they're going on to
Ours are 10%. 10% of your final grade is usually what we assess the project and weight the project as. Yeah. All right. I hope we've gotten you interested in projects today, and if you haven't tried projects in your classes, that you will try them in the future. Please email us with any questions. We'd be glad to share this information with you. Thanks for coming. Have a great conference.